Okay, so this is lecture 22, example 1. So this is the last type of problem we'll do in the class, last really new thing we're going to do. And essentially, it's a problem where I'm going to ask you to describe the modifications necessary to add these new instructions. Now, I really like these problems because essentially you have to know what you're doing to do these problems. Now, it's really easy to, and I've seen it in other courses, to kind of just go through the motions and not really understand the architecture. I think kind of the focus on this class can be programming, and it's not really a programming class. It's more of a hardware-based architecture class. So that's why I emphasize the hardware. You got a world full of programmers out there, and not too many of those people actually have a real strong understanding of the hardware. So this is still a hardware-based class, so I'm going to use these type of problems. So once again, here's what it is hey, you got to add these two new instructions to the RISC-V. Now, okay, so let's look at it. Okay, and then you have to do all this required stuff down here. So essentially, I'm going to have to change stuff. And so what I'm interested in is the change of the hardware, the change in the assembler, and the change in memory requirements. And then there's some generic questions down below, why it's great instruction, and some other thing related to the question. So these are first three questions are pretty much the same three questions I ask for all these problems. So let's do it. So this is, and unfortunately, I'm not gonna type these out. I'm actually gonna kind of talk them out, and I promise you, I just fixed this up in the lab or it's in the text, and I think it's in chapter 19. The solution is in there, so I'm going to encourage you to go look at that solution. And yeah, let's chunk through this and see what comes out here. So we got an instruction, essentially SLL, SRL, which is shift left and shift right, but I put this _1 in front of it. So these are my new instructions. And so best way to describe what these instructions are doing, of course, is with some RTL. So I've described it with RTL up here. So this is a shift left, and I'm shifting left, and I actually, let's see if I get this right, I mixed these up. Okay, so let me quit and fix those. This is the shift right instruction. Let's see what we got here. Shift right logical. So that's going to take the top 31 bits and make them the bottom 31 bits, and essentially stick in a 1 at the top. So it's shifting in a 1, which is where this 1 comes from. So the shift left is going to take the bottom 31 bits and make them the top 31 on the right side. So these are my two instructions. I can certainly, first thing you have to understand is that I'm going to specify these quite often in RTL. Easiest way to do it, typically how instructions are specified. So you have to be able to kind of look through this. And the issue is, it's using for better or worse, it's using a Verilog concatenation syntax as well, so you kind of have to deal with that as well. And it's kind of a pseudo Verilog, but good enough. So those are our instructions. So let's how are we going to do this? And so essentially is we have instructions that shift left and shift right, but they're currently they're putting in zeros, so they're actually barrel shifts. I can shift as many bits as I want, but it always sticks in 0. So what I need to stick in 1, so I have to see if this fits. And so the issue is of fitting it in here is that I have 4 bits to choose the ALU function. I'm using 11 of those, I think. So there's actually 4 unused, 4 or 5 unused. So certainly there's room for 2 brand new shift instructions, and I could just call SRL1, SLL1, which is different from the ones that are already in there. Okay, so I have room for it. I don't have to extend the bit width of ALU funds. Not a big deal. So that's one part of the problem. The other part of this problem is this is from one of the cheat sheets. Is I'm going to try to fit it in a known instruction. So one of the useful instructions is, I mean, this is an immediate type instruction, and so what I have here is I have these immediate values. And I'm going to count them. 1, 2, 3, 4, 5, 6. Look, there's 6 of them. And all these values have the same opcode. So I'm going to try to fit it in with that opcode. And I'm essentially going to add 2 more. The way it differentiates these 6 instructions is with this func3 code. And what you'll see is this is missing a 1, 0, 0, 1, and a 1, 0, 1, a 1 and a 5. Okay, so that means to fit these instructions in the architecture, what I'm going to have to do is modify the ALU and just put the mathematics in there. And on the outside of it, I'm going to add some new instructions. They're going to be I-type instructions. I have room for them, and the way I'm going to differentiate these is by changing this func3 code. So, you know, somewhere in there right now, somewhere in the decoder, it uses the func3. Let's go ahead and look at that. The func3 is these bits right here, and essentially it uses those bits to describe which the ALU fun is for those 6 instructions. Now we have 2 more. We filled up all different func3 codes. We added 2 func3 codes to it. We kept the same opcode, and this is going to work. So that's going to require that we change this decoder as well. So let's summarize this. We changed the ALU to notice 2 more operations, which is good. We changed the decoder such that we made it recognize 2 different func3 codes. We kept the I-type instruction the same, which is good, and we filled it up to all 8 func3 codes. 2 more ALU functions. How about the state machine? Look, I don't need to change anything in the state machine. The control signals associated with the state machine are exactly the same for all the immediate type instructions. This is another immediate type instruction, and so don't have to change that. So once again, really the 2 things we changed are this and this, so the decoder and the ALU. So let's go back to our problem here. So we're kind of done with that one. With the assembler, essentially the assembler, we have to tell the assembler about these new instructions and be able to tell the assembler, hey, it has the same opcode, but it has a different func3 code. So we'd have to essentially notify the assembler of this new instruction so it sees it and sends out the right machine code. So the memory. So what memory have we changed on this one? We'll go back to our picture here. We only changed these 2 things here. Now this is a decoder. It has no memory. It's a combinatorial. ALU is combinatorial, also has no memory. We didn't change the PC, we didn't change the memory, we didn't change the reg file, we didn't change the control and status registers, and we did not change the FSM. Keep in mind the FSM is a state machine and does have some memory in it. So we didn't change any of those. So the only thing, we didn't add any memory. So the memory requirements did not change. So potentially useful instruction, sure. It's essentially, why is it potentially useful? Essentially, if I needed to do an operation like this, I'd actually have to spend 2 clock cycles on it. I would have to do an AND immediate after I was done with this one. In fact, I could do an AND immediate for a shift left. I'd actually have to use a register, which means I'd have to use an extra register to do the shift right, because I can't stick that immediate value in using, I can't put in that extra 1 bit on the left side using an immediate value because it's limited to 12 bits. Okay, and lastly here, why don't I need SLLO and SRLO? Essentially because I can retain that functionality currently with the instructions I have. Essentially, they always shift in zeros. This would be an issue of writing an instruction like SLL immediate X8, X8, and 1. This would be the equivalent. So that's a shift left, and it's going to stick a 1 in on the right. It's going to stick a 0 in on the right side after shifting 1 time. Okay, so once again, I'm going to call this done. These problems are super open-ended, and I always like throwing them out there because I like to see what people write down. And quite often, I get some really good ideas from what people write down, certainly better than my ideas. And there's not any one right answer. It's kind of gives you the option to do a brain dump on these to show what you know. Okay, once again, the solution to this is in the text. I think it's the first problem. You can paw through that. Okay.